I'm Adrien Duadi. My entire life's work in mathematics was centered on the complex number. My contributions helped advance both algebraic geometry and the theory of dynamical systems. Complex numbers have a long history. You see here, on the left, Tartaglia and Cardano, mathematical pioneers who lived during the Renaissance. On the right, Cauchy and Gauss, who consolidated the theory in the 19th century. Complex numbers are not really as complicated as the name might lead you to believe. At first they were called impossible numbers. Even today they are still sometimes called imaginary. Well, it's true, it does take a little imagination, yet today these numbers are everywhere in science, and are not really mysterious anymore. In particular, thanks to them, one can construct beautiful fractal sets, something I worked on a lot. I even produced a film, The Dynamics of the Rabbit. It was one of the first animated films in mathematics. Let me begin by explaining the complex numbers on the blackboard. Mathematicians just love writing with chalk. You'll see in a minute that my ruler, t-square, and protractor behave rather oddly sometimes. Let's draw a graduated line on the blackboard. One of the most beautiful ideas in mathematics is to link geometry to algebra. This is the starting point of algebraic geometry. Just as we can add numbers, we can add points. Here is a red point on the line and another blue one. Let's add these 2 points. We get the green point. 1 plus 2 equals 3. When the red and blue point move, the green point, which is their sum, must move too. More interesting still is multiplication of points. Let's look at multiplication by -2, for instance. It transforms the point 1 into the point -2, of course. And if you multiply once again by -2, you have to do the same thing. Change sides with respect to the origin, and double the distance from the origin. You get 4, of course. If we multiply twice by -2, we have multiplied by 4. Multiplying by -1 is very easy. Each point is sent to the symmetrical point with respect to the origin. In other words, we do a half turn, a rotation by 180 degrees, if you like. When we multiply a number by itself, the result is always positive. For instance, if we multiply by -1, we make half a turn, so that if we do it one more time, well, we come back to the initial point. This is why -1 times -1 equals +1, simple enough. You see, for instance, that multiplication by -1 sends 2 to -2, and that if you multiply one more time by -1, you come back to 2. Obvious, isn't it? Therefore, there is no number which, multiplied by itself, yields -1. Another way of saying this is that -1 has no square root. But of course, we are underestimating the inventiveness of mathematicians. At the beginning of the 19th century, Robert Argand had a really great idea. He said to himself, since multiplying by -1 is a 180-degree rotation, its square root is a rotation by 1/2 of 180 degrees, 90 degrees. If I do 2 quarter turns, one after another, I end up doing a half turn. The square of a quarter turn is a half turn, hence -1. It's easy when you know how. Argand decided, therefore, that the square root of -1 is the point where 1 ends up after a 90-degree rotation. But of course, this forces us to leave our horizontal straight line, since we just agreed to assign a number to a point that's not on the line. Because this construction is a bit strange, we call this point, the square root of -1, an imaginary number, and label it I. But once we have the courage to leave the line, everything else is easy. We can represent 2i, 3i, and so on. Each point in the plane represents a complex number, and conversely, each complex number defines a point in the plane. Points in the plane become numbers in their own right. These numbers can be added, just like usual numbers,